Welcome, everyone. Sorry for a little bit of a technical glitch there, but welcome to the NCDS DataBytes Lunchtime Webinar Series. This is our first webinar for 2018. And today's speaker is Theresa-Marie Rhyne. Theresa-Marie is an expert in the field of computer-generated visualization and a consultant who specializes in applying artistic color theories to visualization and digital media. She has consulted with Stanford University Visualization Group on a color suggestion prototype system and with the Center for Visualization at the University of California, Davis, and the Scientific Computing and Imaging Institute at the University of Utah on applying color theory to ensemble data visualization. Her book called Applying Color Theory to Digital Media and Visualization was published by CRC Press on November 17th of 2016. And since then, she's been lecturing and teaching tutorials on this topic. Prior to her consulting work, Theresa-Marie founded the Center for Visualization and Analytics at North Carolina State University. And she also served as director of the Renaissance Computing Institute's Engagement Center at NC State. Today's talk, which is titled Applying Color to Visual Analytics in Data Science, will last about 30 to 40 minutes with time for Q&A at the end. Please type your questions in the chat box, which is our usual way of doing things here, and we'll hold those questions until the end, read them back to the speaker, and get them answered. So without any further ado, I want to introduce Theresa-Marie Rhyne and welcome her and welcome all of you. Take it away, Theresa-Marie.
So today we're going to talk about applying color to visual analytics in data science. And we're going to highlight 5 topics: introduction to color models and wheels, review of color vision principles, defining color gamut spaces and systems, exploring color harmony, and tools, research, and case studies related to color analyses of visualizations. So let's do a review of some key color models that many of us are probably already familiar with. We have the red, green, blue color model that adds lights. That's what we're displaying on right now. We have the cyan, magenta, yellow, and key black color model that we use for like our inkjet printers. And then we have the painter's color model, which is red, yellow, and blue, that we often see when we go to a museum and we see paintings. So it turns out we can define an inverse relationship between Rgb and Cmyk, and that relationship is as follows. Oop, a little too fast on the trigger here. Let me get this back. We'll get it back. So there's our color models again. And now we're going to look at our relationship again. So this is Rgb, Cmyk, and as you can see, red and cyan are complementary to each other in this model. Blue and yellow are complementary. Green and magenta are complementary. So if we look at the summary across here, we can see if we had a pure world, what would happen is that we would shoot something on our mobile phone and we would get a perfect printout on our inkjet printer that would match the colors and transfer. But as we all know, it doesn't work like that. And what happens is very often when you transfer from an Rgb color space, a display color space, into a printed color space, Cmyk, we get things that are a little bit off. Sometimes the pinks, magentas are a little duller here. Sometimes the greens are a little duller. There are differences. So this is a comparison here. Now, let's consider some historical views of the color wheel. The color wheel was first defined by Isaac Newton. When he looked at the color spectrum, he basically turned the rainbow color wheels into a circle and made us a color wheel. And then that was in 1666. In 1810, Goethe defined complementary colors. And this is Goethe's first color wheel right across here. He's going colors across from each other right here. And he also is attributed to having put magenta on the color wheel because magenta is not a spectral color that's part of the rainbow color map. Chevreul was the first person to study simultaneous color contrast. Chevreul was a chemist, and basically he was hired by people in textiles because certain colors, if they were combined together, even though they were pure, they looked faded next to each other. And he developed the law of simultaneous contrast, and we're going to look at it here. Notice how even though these squares are the same size, they look a little bit bigger or smaller than each other because these two colors are directly complementary to each other. He wrote a lot on this in 1839 and published a lot of material. Now, how do we use this? We use this when we do a visual analytics. We want to make sure that we don't put these colors inside of each other, but around each other. See here, they are complementary across on a color wheel. And this would be how we would develop a tree map right across in here that emphasizes it. So now let's talk about some color vision principles. We have the trichromatic theory of color vision, the opponent process of visual perception, and we have the coexistence of these two theories together. And then I'll talk a little bit about color deficiency when one of our cones in our eyes does not work properly. Okay, so trichromatic theory was first hypothesized by Thomas Young in 1802 with no experiments. He hypothesized that our eyes have 3 different cone cells in them. It would not be until Helmholtz, von Helmholtz in 1850, he classified our cone receptors, and here they are. There's the blue, the green, and the red. Now notice, long preferring is red, medium preferring is green, short preferring is blue. Now notice, when you say that someone's cone doesn't work properly, it's not like, as I tell many of my students, it's not like a cell phone where the red monitor went off. What it is it means for our eyes, it means that the red cone is seeing a broad range right down in here. So you see, actually your red cone sees a little bit of violet, sees a little bit of green. So it's not a perfect red, green, blue combination. So color vision in 1878, Herring said, well, it's a little more complicated. Now think lights for me right now. Think lights. Don't think that these two colors mixed together as paints that you can see them. But Herring challenged Young and Helmholtz and said that we have 3 channels of vision. Red and green. These lights do not combine together in the world. He said, blue versus yellow do not combine. You don't see bluish, yellowish combinations. You don't see reddish, green combinations in light. And he also pointed out that black and white have different combinations that we see in various light combinations. He said opponent colors are not perceived together. So he defined a 4 primary color system across in here. Now, it turns out that Helmholtz accused Herring of being crazy, not able to understand what was going on with regards to the vision in our eyes. It would not be until 1957 that Hurwitz and Jameson, working for Eastman Kodak, would put qualitative data out there, quantitative and qualitative data that supported Herring's opponent color theory. They said that you can combine hue cancellation methods and show that red and green lights mixed together actually produce yellow. That blue and yellow lights produced together produce white. Now think about it. We know that red, green, and blue produce white. So red and green would be yellow. So yellow and blue would produce white as well. So red and green cancel each other, as do yellow and blue. So you can start with a bluish green and add light to cancel out the blue light and produce only green light. So this was critical in terms of trying to understand how cameras work in camera culture, actually in the late 1950s, early 60s. And now we can sort of see this when we have projectors and display devices. Now, let's talk a little bit about color vision weaknesses. When there are three of them, protanopy would be your red cone is absent. Deuteranopy, which is the most common, would mean your green cone is absent. Tritanopy would be your blue cone is absent. Tritanopy is increasing because in some types of cancer treatments, the blue cone gets a little affected with a lot of radiation and things, and this actually is increasing. So this would be a pie chart of the color wheel colors across in here. And if you had a color deficiency, what would happen is you couldn't tell the difference between red and green. You might have a little trouble with your oranges in here. You probably could do yellow and blue pretty well, but blue and purple would be a little confused. It's also very similar. Deuteranopy and protanopy has some very deep similarities, but basically we want to design with these parameters in mind. This is VisCheck, is a simulation software that shows us how people with color vision weaknesses see this particular pie chart. So it turns out one of the more popular topics in dealing with color in visualization, specifically scientific visualization, has to do with a rainbow color map. For a long time, visualization systems presented a color spectrum as their default that went from red to purple across in here. However, it was shown to be misleading, especially in people like in medical visualization as they're making decisions about tumors. Notice this yellow range is much smaller than this green range right across in here. So it was shown to be prone to certain errors. There was much discussion about this, and there's still a lot of discussion about this today. A lot of research is still studying what this impact is about. But however, if we look, this recent color map work has tried to change the default color map, and Matplotlib and various other mathematical visualization tools to what they call Veritas, which begins with a sort of a deep blue purple, goes across to a deep yellow. And this has become the default color map because it's turned out to be a much more effective solution for presenting data across its broad ranges. So let's get some references. Lloyd Trinish and Bernice Rygos were the first to report some of these concerns in 1998. Here at Chapel Hill, David Borland and Russell Taylor studied this in 2007 and re-emphasized its importance. Then we have Kenneth Moreland recently in 2016 providing advice. And Colin Ware and his team at the Department of Energy Labs in Los Alamos actually did an evaluation of this and reported the results in 2017. So let's look at some color spaces across here. How is it that color gamut and color model produce a color space? We're going to talk about perceptual uniformity. I'm going to talk about this is a color space that's independent of your device that you have in your hand. Hue saturation value, critical to computer graphics, WebHex triplets for designing a web page, and how designers match with Pantone. I'll also say that there are indeed several apps on your phone for this. Okay, so when we look at color gamut, this is the particular relationship defining color gamut spaces. It's for, this triangle right down here is the typical sRGB space that's on a particular mobile phone. This is usually about the default system of a mobile phone. This horseshoe represents the complete gamut of colors that our eyes can see. And you can see this triangle right in here represents what is called sRGB device space on a mobile phone. So we can look at several RGB spaces. Matte paper right in here would be the CMYK printing paper, and you see how it's outside the sRGB space, and you can see exactly that diagram I showed you earlier. This is what's being produced right across in here. Adobe tried to address this in Adobe Photoshop and its Adobe Premiere tools by making an Adobe RGB space that spanned the entire elements right in here. And you see it's trying to encompass both of these elements so that what you see on the screen you can pretty much print or transfer pretty transparently for what's on the screen to video or to paper. Pro Photo RGB is what photographers use. Kodak developed this. Now notice this triangle is so large that it's outside the horseshoe color spectrum. So it is possible to shoot in raw camera on your camera colors that we can not actually see. So this is the comparison of these color spaces. Now it turns out that CIE-XYZ, this is a commission on color, the Internet Commission on Illumination, developed CIE-XYZ in 1931. With what they did was they did experiments, perceptual studies, and they defined this horseshoe and this relationship, and this is device independent. So if we look at this particular, if it's used for color and calibrating displays and printers. So how did they match these? I always wondered, how do they do the experiment? So they have someone that's called the observer, and they look at a test lamp. So that we'll have them look at yellow, and they're going to turn a bunch of knobs here and try to match that yellow as much as they can. Now, if you read the literature, there's a whole bunch of techniques. You can add, subtract. There are all kinds of equations and formulas to try to match a color, but we'll just keep it really simple. This is what's going on. And then they also test beforehand to make sure that they do not have color deficiencies. So this is actually how the data is gathered for these experiments. Okay, so it turns out the chromaticity diagram has some important elements for us to try to understand. So we have all the visible element colors, it's in this horseshoe. Then we have the edge of the diagram is called the spectral locus, so that's right across in here. The least saturated colors come into the center. There's always a white point in a chromaticity diagram where all the colors come together and produce white, like we talked about, this RGB combining together. Now, it turns out this diagram is actually representing a 3D space because there are equations right down here that relate all these together, even though it's projected on 2D space. Any two colors are gone along a given line between 2 points are made by mixing the colors. So I'm going to use this line. It's actually called the line of purples. Between here and here, if I pick this point, you're doing a combination that mixes this to produce magenta. So it's saying blue and red together will get us a magenta combination. This is called the line of purples across in here, by the way. It's a specialized line. It turns out that this 1931 color space, we look at it, was heavy on the green side, very heavy on the green side. And a lot of people published articles, a lot of researchers in color science published articles expressing concern about this over the years. So we get into the 1970s, and they proposed two different color systems. CIE love, you're either going to love it or you're going to lab it. This color space is new experiments, and you'll see they're showing another color space that's more on the blue side and has reduced this green element. This particular color space was actually CIE lab. There are people that have built chromaticity diagrams, but it's actually not accurate to use one to define that color space, but it's a opponent processing color theory. It's hearing revived again right across in here. There are many equations associated with this. These slides at the bottom of it are some references to where you can find more information if you want to study this. So this is our 1931, this is our 1976 diagrams right across in here. Now, what happened in the 1990s, there was a tremendous effort to try to address color appearance models, such as the image on a display and its resulting hard copy reproduction combined together and matched them more correctly. And this is called CIE CAM97 was developed as the interim model to address this. And now CIE CAM02 happened in 2002 to improve it. This is a moving target. Just think about the fact that every time there's a new device, a new cell phone that comes out, this color appearance can change. So presently, CAM02 is called state of the art. And here's the reference. I have been told that these slides will be put online. So if you want to really study all these equations, there they are. This is the reference that does it all. So how do we use this? What is this all about? Okay, here's what it's all about. When we talk about cell phones, Apple uses something called wide gamut color space. You have to listen really carefully when Tim Cook and his vice presidents are up there talking. But if you listen really carefully, they're saying that they have a wide color gamut bigger than sRGB. So this is sRGB. This is Adobe RGB. This is a color gamut that's sitting on the iPhones from about iPhone 6 up into iPhone 8. So one of the challenges photographers have gotten in it, Apple chose to work on the cinema standard. That's called DCI P3 versus working on the photography and field, which would be Adobe RGB, like Photoshop. Think of Adobe RGB as in Photoshop. Some photographers have been a little upset about that fact because it means your cell phone is not always the best for shooting a still image. So let's compare the color space. This is the iPhone 10 color management system, display modes. My colleague, I have a colleague that actually calibrates all of these for a living, and I'm showing you his tests that he's done. And he's saying that Apple switched from the liquid crystal display, this is your iPhone 8, this is just between iPhone 8 and iPhone 10, to organic light emitting diodes, OLED displays, so LCD to OLED displays. So that's what you're paying that extra money for that they keep talking about being so expensive. And it's considered to be 100% DCI P3, precision display calibration. So it's 100% sRGB for color management. The phone automatically alters back and forth depending on what you need to do with regards to, if you're shooting a movie, for example, it's going to stay in DCP3. If you're working on a web page, it might go to sRGB. So here's the competitor. Samsung Color Spaces, their Galaxy S8 phone actually did this before Apple's iPhone 10. They have an adaptive display technology, which is 142% greater than sRGB, 113% DCI P3. They call theirs AMOLED cinema and photo. Now what they do is they automatically convert between the two. So they can support both photo and cinema and basic screen mode. So now let's compare the two. Now in test, the iPhone X is presently considered to be the best one that maps right across in here, but Samsung's Samsung's prior phones are really close. Now this is the battle between when they released two phones on top of each other. And of course, interestingly, OLED displays. Who makes OLED displays in its raw manufacturing? Samsung. So it's a tight battle between these two. And this is what's going on every time they're trying to improve their particular mobile phone devices. So how do we calibrate displays if we have a laptop and we want to know how? There's a thing called ColorMonkey display calibration devices made by X-Rite, and there are other competitive companies that make this, and this calibrates what your display is about, just so if you want to know what it looks like. So let's go back in time and talk about hue saturation of value and hue saturation and lightness models and their importance. They were cylindrical coordinate representations, they still exist today, of the RGB model space. It turns out actually there was an earlier prototype called hue saturation and brightness, HSB, that was developed in the late 1800s, early 1900s. And in the early days of computer graphics, many of the leading researchers would go back and read older scientific publications and see how they could put it into the digital world. And this is their version of hue saturation value and hue saturation and lightness. So it was developed in the 1970s, published in 1978. Here is the issue. You have a display and you have yellow here, and you want to make it slightly dull it. You want to dull the display. You want to add a little bit of gray to it. It turns out if you stay just in RGB space, you'll get it -41, -31, and 21 plus for blue. That's not intuitive. So the idea was to develop color spaces that was more intuitive. Alvy Ray Smith came up with the first one. By the way, Alvy Ray Smith is one of the founders of Pixar, if that is of interest to you. But he defined hue as your particular color selection. And he says, hue is the most saturated on the outside and goes into white as you move into the inside. He says value is lightness or darkness of a given color, overall intensity, and basically develops a cone right down in here to define this. Then the same year, Joblove and Greenberg developed hue, saturation, and lightness, which is a double cone. It's this element and this element down in here that tries to combine the colors. Now, why do you care? You care because the Web 3D Consortium adopted this standard when it comes to web hex values. So it means if you use hue, saturation, and lightness values inside your coding for a web page, it will automatically take the values even if you don't have the hex triplet or the RGB value. That would be why you would care. So for web colors, again, they're doing hex triplets. So a byte is a number from 00 to FF or 0 to 255 in decimal notation. So byte 1 is red, byte 2 is green, byte 3 is blue, RGB right across in here. If any one of the values is less than 10, it must be replaced with 0. So this shows you how you get your hex triplet values right across in here. Now, independent of any of this is Pantone. Pantone in the 1950s, there was a fine gentleman who decided to paint colors on pieces of cardboard and send them out across the world and say, okay, if you use these pieces of cardboard with a color painted on them, you can describe the color better than if you describe it on the phone. So you're in Los Angeles and in London. So we're in the 1960s. So we're going to talk about the Beatles just because it's a good one to talk about. So the Beatles are going to come over and travel around the United States, and the people in Los Angeles have to print all these posters for the Beatles to come. And so over in London, they describe particular colors of that the poster should have in them. If they describe it over the phone, the chances of them matching this particular paint correctly is not so good. However, if you have pieces of cardboard with the same paint painted across them and you call it Pantone 3527 color coded paper, you can match it because the guy says, oh, I have that same Pantone color coded paper in my fan across in here. And this is how the Pantone system, and it began as a color matching system exactly in that way. By 2001, Pantone began providing digital translations of their RGB values. So where do you want to use this? Well, we'll talk basketball for a second. There's a big difference between Kentucky blue, Carolina blue, and Duke blue in basketball jerseys. And I promise you, many of the athletes know their Pantone color. And they need to know their Pantone color because when they have to use different jerseys, different transferred into cups, transferred into various paraphernalia associated with going to a basketball game, you need to know what that Pantone color is going to be. It's amazing how many athletes are extremely knowledgeable of Pantone values. Okay, so we're going to use this for visualization. So you have on your phone a particular visualization, this particular one, and you want to tell somebody how to print the molecular biological visualization that you have in Pantone colors. So you pull out your Pantone Studio app and you find the purple and you find the green and you specify it for printing those particular colors. So there is an app for it. So now we're going to explore a little bit about color harmony, because what I just showed you, that purple and green back there, that's an actual color harmony concept of complementary. So we're going to create a color wheel. We're going to talk about hue, tints, and tones and shades. We talked a little bit about that in HSV and HSL. And then we're going to understand some of the harmonies. So this would be our first color wheel. This would be RGB. Then we're going to go across in here and then we're going to add cyan, magenta, yellow. By the way, the reason they use key black and cyan, magenta, and yellow and key black is because to try to have these three colors over top of each other over text, you get blurred registration of the printed text. So they ended up adding black, which is the key black, into the printing model because there's often more text than color images in a particular book. Anyway, these are our primary and secondary colors right across in here. Then we can add more tertiary colors to get more color elements if we want them, right between these two. And then we're going to put a neutral gray zone, or you can put a white zone, a zone in the center of the color wheel. So now we're going to define some hues and tints. So the hue is the purest color right across in here. A tint means usually people add 50% white inside a color. So if you add a red and you put a 50% white, get some kind of pinkish red across in here, these are considered the tints. In a precise definition, you can add 1% to 99%, but usually it's 50%. A tone is adding 50% gray or a percentage of gray to an original hue. And a shade is adding 50% black to an original hue. So this would be how our color wheel might look if we combine them all together. Solid, our hues, our tints, our tones, and our shades, and our gray center. So this would be an Rgb CMYK color wheel. So now I'm going to talk about color harmonies: monochromatic, analogous, complementary, split complementary, dyad, triadic, tetradic. Now, I am only going to cover 3 for this particular class because it would take me a little bit longer. I teach a longer class in my tutorials at conferences and things, but here we're going to talk about monochromatic. So this is your hue, tint, tone, and shade. So what we're going to do is we're going to build a visualization, a pie chart visualization in the key of yellow. This is the yellow that is all of these combined together. Now, this is something we often see in various financial publications. You'll usually see this in blue or green. So monochromatic. Analogous is picking 3 colors next to each other on the color wheel. This one I'm going to stay in the key of yellow, and then I'm going to put orange and yellow-green next to each other, and I'm going to do a bar chart visualization. So this is an analytics visualization. Now notice what I've done is I've added the 50% gray to create a shade across in here. Once you start to see these tricks, you realize that fashion designers do this all the time. They add a little bit of, for men's clothing, they tend to add tones and produce the coloring and tones. For women's clothing, they'll actually add a lot of, they'll come up with pastels, which is adding a lot of white to the color. So complementary are 2 colors across from each other. So we're going to talk about blue and yellow. And notice how this is a shade right in here, and this is a shade, and this is a particular analytics graph. Now this is an interesting color harmony, just that's not often used. Some people relate it more to an Asian type of culture, and this is taking a color that is one off from, so you have it in the key of yellow, and you take the red and you combine. You can get a bubble chart like this. So if you want to have something a little different. So it turns out there's a whole lot of tools out there that do automated color analysis. So we're going to look at a Monet painting that's at the North Carolina Museum of Art. So if I want to understand how did Monet, what color palette did he use? If I look very closely, he used, whoop, I got a little jumpy on it. He used, come back, baby. Well, I want to tell you that he used white. Oh, I've gone way, 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 way off, but I'm pushing it. I'm going to push it a little more. Let's see, like now we're going to have a review of what I just did. Spontaneous review, everybody. So let me see if I can move it fast. All right, so remember I talked about tints. Then I talked about tones and shades. Woo! Did I get far down here? I'm going to escape for a second out of my talk, try to get myself back to where I was. Okay. All right. So now we got Monet here. We want to see what our painting is. And if we look carefully in this color analysis on the color wheel, we'll see Monet stayed right around the white area. So he was what they call a plein air painter, which means he mixed his color on the fly as he was looking at it. So you can see what he's doing is he's got a lot of white and he's combining these colors together and he's adding white across down in here to get a palette change, small changes right across in here. Now I want to talk about Color Brewer because it's often used a lot in visual analytics. Color Brewer is a tool developed by Cynthia Brewer and Mark Harrer at Pennsylvania State University for the GIS community that's actually found its way into the visualization community. Maureen Stone, when she developed the first Tableau software color maps, used it. And you'll also find that Tamara Munster, who has one of the leading books on visual analysis and design, uses sequential, diverging, and qualitative color map schemes and classifications in her work. So this work goes all the way back to Cynthia Brewer's sequential color schemes, diverging color schemes, qualitative color schemes. So a sequential color scheme is an awful lot like a monochromatic and analogous color scheme, that what a single hue would be a monochromatic, a single hue with tints, tones, and shades. Then right in here, she uses colors that are very close to each other on the color wheel to complete this sequential multi-hue. Right in here, her classification system for diverging is, these are close to complementary, not pure, but some of these are close to complementary on the color wheel. And this is just across the board for her qualitative color schemes. So optimized for ordered data from low to high is sequential, places diverging, places equal value in the mid-range for extreme values, and qualitative does not apply magnitude differences. So here's a particular example. We take this particular color scheme, this diverging color scheme from Color Brewer, and then when we apply it to this particular visualization, notice color quantity makes a difference. So the visualization looks a little bit different, but this is how we create this and how we use Color Brewer. So we can use the same thing for infographics across in here. So just to sort of see how Tableau did it, this is the Tableau Classic. And what they did was they took Brewer's color maps, then they developed a new color in Tableau 10. Recently, in about 2016, they did a new color mapping. And this is their classic and their new. They have an article written on it if you wanted to research it further. So the redesign of the default color maps uses tints and tone elements to create more direct hues. So that goes back to what I covered earlier in my lecture. So where does this relate if you're in this world of Tableau? It means it used to be that this was your default. It was green was your default, and today your default is blue if you're developing a color palette. It also means that previously your default was red and green if you had two data sets and you were comparing them against one another. Today it's orange and blue. And you'll notice they factored in color deficiency weaknesses because they tried to get away, when we talked about color deficiencies, they tried to get away from this idea being that if you had a color deficiency and try to present it with this idea across in here. So this is what would be the default today. This is what was yesterday. So now I want to cover some recent trends in computer graphics and color research in the VIS and computer graphics community. Now these are articles, so I'm covering it. 2017 was a pretty exciting time for color. So this was done in October. This actually was the InfoVis paper, the award-winning, the best InfoVis paper was on modeling color difference for visualization and design. This particular one was also presented extracting and retargeting color maps for bitmaps and visualization. This particular work, it talks about the SciViz community, and I'm going to show you an example of their work right a little bit later in my slides. This is Adobe's latest work talking about playful color maps for artists. And this work should be coming out further into probably 2018 as tools. This particular one, this is new work presented at CHI. This is looking at how color affects our moods and how color affects our decision making. And this is relatively new work that should come out further also in 2018. So now I want to talk about, right now, deep learning is a very hot topic right now in the visualization community. And people have used deep learning to colorize photographs. Here's my example. I have a black and white, I have a color photograph. I went to black and white here, and I've shown how this particular tool will colorize. Now you'll notice some differences. The original had a sort of brownish bales of hay, and this one did greenish bales of hay. But the research actually goes through and takes black and white photographs that were done the Depression era, that was only black, and tries to show how they would create colorized versions of them. But this particular tool is available online if you want to take any of your own color tools and use it. But this is very exciting, the research that's coming out in terms of supporting how to colorize large data sets and large elements. And right now they're working in the photo area, but they can work with data elements too. So this is another tool called Colorgorical that actually is a perceptual tool. It was introduced in 2016. It tries to give you recommendations and various color schemes that you can use that are perceptually using CIE Lab and CIE Love with regards to its color space. This is where you can get a hold of this tool. It's a pretty good one. This is an example of what I did was I took some Pantone colors and used the Pantone app and put these values in there and create a colorgorical example of to show what this would look like as a visualization. Color Map Hospital was done in the United Kingdom. It's presently not online right now, but basically you can take this is a complementary color scheme. I'm showing it to you in an Adobe Color, which is another tool that's available online. But basically this Color Map Hospital will try to correct it optimize it for visualization. It makes recommendations. Now here's the one you want to look at right here. This should look like a flag to you. Could be France, could be United Kingdom, could be the American flag. You will notice, it turns out that our forefathers were very, very knowledgeable. This particular color combination, people can see no matter what their color deficiency is. And our Star Spangled Banner says, okay, oh say can you see by the dawn's early light what so proudly we hail. And it's talking about the American flag right here. And it shows how this particular color scheme people can see this through tremendous difficulty, battle, and those types of things. And that's why these countries have very often used this particular color scheme. But it's interesting to see in terms of an analytic approach that it shows you this is an ideal color scheme to use in color vision. This is Color Map Hospital again, trying to correct. Again, notice how it corrects it right across in here. This is an actual visualization of a rug in the Baltimore Convention Center. I took this, colorized it, and this says how it would be approved as a visual analytics. Okay, so you can get this information online. This is the folks at Los Alamos. They have a tool called Color Moves where they can take fluid flow visualization and colorize it right in here to emphasize particular patterns in the fluid flow. It's a pretty powerful tool if you're interested in it further. This is they can take climate data as well and visualize it. So now I want to cover something that I did a long time ago when I was at Renzi at NCSU. I want to talk about colorizing a hurricane. And I want to actually present it, rather than presenting it in terms of what hurricane it's modeling, which was the perfect storm, I want to talk about how the color scheme was created. So it's a 2-kilometer grid resolution run with a weather research forecast model. In doing this visualization, we did color Brewer right here. And what we're trying to do is we're looking at this color map and we're going to try to force the visualization tool to create it in terms of, create these colors in terms of the final visualization. So we're not exactly, it's not a perfect match. So what we have to do is we have to combine these particular colors. We're kind of like painters. We're combining this magenta and blue. We're going to combine that color together. The data is going to force it so the pixels come together, and what you see is this purple, which was what this color scheme was. Then we're going to lay on top of it the wind vectors that meteorologists need to analyze. In terms of color theory, what we have is an analogous color scheme right in here for these colors that are coming together to create the purple. And then what we have in here is what is called a complementary color scheme, so that the orange vectors are going to stand out wherever they lay on the map. So we use Color Brewer to develop this visualization. And here are the elements right across in here that I talked about earlier. Analogous, complementary color scheme puts this visualization together. And the animation, when it comes together, you see the swirling purple comes together, but it's the actual data is mixing. It's mixing these. So we're applying color theory across in here. So here's my book. And just for listening to me, if you want to go buy the book, you can get it for a discount. I think there's a slight discount code that you can use at 20% off. And just so you're up to the moment, the color of the year from Pantone, every year around November, Pantone says, so in November 2017, Pantone had a big webinar where it described what it selected as the color of the year, and it's ultraviolet. This is myself in the color of the year. And I thank you for listening to me, and I thank all my friends that have helped me through the years. So I'll take any questions or anything now if there are any.
Looking good in that ultraviolet dress, by the way. We have one question here from the audience I'm going to read back. And that is there any direct connection between the color theory you're covering now, such as complementary colors, etc., and color vision deficiency?
Yes, there is. I'll go back. I'll pull that across here. Okay, so I covered complementary colors like the question asked. So here's our color deficiency. So the issue is complementary, red and green is one of the more key complementary colors, and you're seeing that if you have a color deficiency, you can't see that. And so why is that important? It's important because very often people who are regular color sighted or see all colors tend to try to use a complementary color scheme to emphasize their data. And if you have that color deficiency, you're not going to see it. And this happened to me in my work at the Environmental Protection Agency in the 1990s. I'd used green and magenta, and I was visualizing Lake Erie pollution. And the scientist said to me, I can't see the line on that graph. And the reason was this individual was red, green. He actually had deuteranopy, colorblind. And when it came into magenta in those particular ranges, he wasn't able to see the line being drawn in the animation. So what we did was we made it a blue line. So even though what he was seeing was a green graph right in here and a blue line. So actually we couldn't apply we applied an analogous color scheme to address the color deficiency rather than a complementary color scheme. I hope that explains it. So the deal is you want to be very careful if you want to make sure with regards to color deficiencies that you limit your use of complementary colors where someone can't see it. I hope that answers the question.
Yeah. Okay, do we have any more questions from the audience at this time? And I know we've gotten a couple questions about will these slides and information be available online? Yes, we do post our all the webinars on the NCDS website. Just go to datascienceconsortium.org into the webinar section of the site, and you will find them there. Usually takes us about a week to get new ones uploaded. So if there's no more questions, I'm going to thank everyone for being here. Theresa-Marie, thank you especially for presenting this talk today. We appreciate your time. We appreciate the time of all of our attendees. For everyone in the audience, keep in mind that DataBytes is a monthly lunchtime webinar series. Mark your calendars for our next webinar, which will be March 7th, again at noon Eastern Time. Thanks, everybody, and have a wonderful rest of your day.
Thank you for the opportunity, and thanks for listening to me. Okay.
All right, thanks.